Hey everyone, today we're reviewing the definite integral in class, and I just wanted to take a couple minutes to make a quick screencast about important things I want you to understand as we move forward. The first thing we talked about in class, so this is a bit of repetition, but bear with me. The important thing to remember about definite integrals is that we've got a function on an interval. The function here, I'm going to call it f of x, is continuous on the interval ab. And another important thing is that the endpoints are finite numbers. You can't have plus or minus infinity. Also, because our function is continuous, we can't have a vertical asymptote on the interval from a to b, because that would make our function discontinuous or unbounded. There's a process that's associated with definite integrals that I also want to review, and it leads us to this interpretation, or rather, it comes from this interpretation of the definite integral as an area under a curve. So looking at this picture, if I were to identify the area under the curve, it's this region, this red region. So it's not just under the curve, it's between the curve and the x-axis. This area can be calculated as this definite integral. So let me review where this integral formula comes from. So there's a process. The first step in the process is to partition the interval AB into n subintervals. Of width delta x, and delta x is going to be b minus a, the length of the interval, divided by n. When you partition the interval in that way, and I'll put each of these points, the endpoints of the subintervals, they're called partition points. So we get n plus 1 partition points when we have n subintervals. And it's always the case that a sub 0, your first partition point, is the leftmost endpoint of your interval, and x sub n, your biggest partition point, is the right endpoint of your interval. It's also true that you can write the ith partition point as a plus I times delta x. And that reflects the fact that you can get to the ith partition point by starting at a and then adding I copies of delta x. That's what this formula means. Moving on, let's take it to the next step. So we have the partition points, and what we do from that point is, let's call this inner point partition point x sub I, and this next one, well, let's call these x sub I minus 1 and x sub I. At each partition point, we get a point on the graph. The point on the right is x sub I comma f of x sub I, and the point on the left is x sub I minus 1 comma f of x sub I minus 1. The area under the graph equals the area of all these strips that we make over our partition. But we don't have a formula for the area of a strip like that. It's not something you see in high school geometry. What we do have are rectangles. So if I draw that rectangle in there, and it's a rectangle on the ith subinterval, and let's say it has area AI, then the area of the rectangle I drew above there is its height, which is f of x sub I minus 1, times its width, which is delta x. This is an example of using the left endpoints of each subinterval to calculate an approximate area. And this is what you might call building a left Riemann sum. So the total area under the curve is approximately equal to the sum of all these rectangular areas. And that's our Riemann sum. That's where the Riemann sum comes from. If I was doing a right Riemann sum, the formula would be slightly different. It'd be the sum as I goes from 1 to n of f of x sub I delta x. So this process of building is important. It culminates with the last step. I think it's step 4. If step 3 was building the rectangles, step 4 is taking the limit. The limit, as n goes to infinity, the number of rectangles goes to infinity, of a Riemann sum is that. And this is exactly the definition of a definite integral. This is something calc students often forget, that this is the definition. Shortly after we learn this, we learn about the fundamental theorem of calculus, which gives us another way to calculate this. But and we're more likely to calculate it that way. But this is where Riemann sums come from. And this 4-step process of cutting up and adding up, we'll repeat that many times this semester. I just wanted to put that back out in front of you. All right, thanks for watching.